Okay, hi there. This is Dr. Matthew J. Trom. We are now doing lecture four, still in module one, which is focus on conduction. And this lecture is one-dimensional steady state conduction. This corresponds to reading in the textbook most of chapter three, plane wall, alternative conduction analysis, radial systems, summary of results, and conduction with thermal energy generation. There is a sixth and seventh section to this chapter, and we'll do at least the sixth section in the next lecture. So at least get this far in your reading, please. Okay. Oh, the other thing that I want to mention is I'm obviously recording the video right now, so I don't yet have an ADA compliant transcription. But when I finish recording, Zoom will presumably create that for me. And so if you need the transcript, there'll be a link here, and you can click on the link and get to the transcript in case that's something that you need. Let me get my laser pointer up. There we go. Okay. So as you guys know, I like to start lectures with a meme or a cartoon or something. And I think you guys have, at least the ones who've had fluids with me, have seen this one before in a different context. But this one, Game of Thrones meme. And I've crossed out the word winter and I put quiz one because quiz one was released over the weekend, so a couple days ago. And you guys still have several days. I think originally my plan was 7 total days for each one of these quizzes, and this time around I gave 8 days. Um, so just one little extra day in case there's any snafus or anything. So just be aware that there is a quiz that's out there on Canvas, and you should be solving the quiz like this week. Please don't leave it to the last minute because it is, I think, hopefully a little challenging. I hope. Um, so don't leave it to the last minute. Please, take a look at it and try to tackle it. Not right before it's due. I will just quickly mention that it is totally fine to use AI. In fact, if you're not using AI, you're probably doing something wrong in 2026 because engineers use AI as just a standard tool like out in engineering practice. And so I think it's crazy for engineering faculty to say, no, you can't use AI because engineers do it. You're also welcome to talk to each other, right? That's fine. Phone a friend if you need to. The only thing that we ask is that like the final product is your work, right? So you're going to make a 4-minute video, recording yourself explaining your solution. Make sure on Canvas that you upload both the video and your written script. It doesn't have to be handwritten, right? If you want to like code it into, I don't know, some sort of, handwriting to text conversion thing, that's fine. Um, but we do need both a video and then some sort of like written out document that describes your step-by-step process. And really what we're looking for in the video is that it's you doing the explanation, right? So I know, some of you guys are like, super, AI gurus and probably can come up with a talking head of yourself, like an avatar of yourself. We don't want that. We want to see you. So the uncanny valley still is hopefully, at least this semester, human detectable. And so that's kind of what we're looking for to make sure that it's you and not some AI version of you. And we're also going to, just kind of watch your mannerisms and watch your presentation cadence just to make sure that you're not reading off of a script, right? It's fine to have a script, but if you're sitting there like, I am reading off of a script. I am a robot, and AI wrote this, right? And it's very clear that you're not doing any of the thinking, that you're just reading off of an AI generated script. There will be some consequences for that. So please just make sure that it's you giving the explanation and it's your thoughts and your ideas. Fine to use AI, fine to phone a friend, but please make sure that what you're presenting is your work, and not the work of a robot or someone else. Okay, let's jump into the lecture. So this is like a summary of where we're going, and boy, there's like this is like alphabet soup. There's a lot going on here. And weirdly, this table is like if you go back to like the reading list, it's given here, right? Summary of 1D conduction results. I don't know why they don't start with the summary of results and then explain where they all come from. But so this is essentially just a table of all the things that we're going to talk about. So we're going to talk about the various forms of the heat equation, the temperature distribution equations, the equation for heat flux, heat rate, and thermal resistance for three different geometries, for plane wall, cylindrical walls, and spherical walls, all as part of one-dimensional steady state heat transfer solutions that involve conduction. And I say here with no generation. There is actually a generation section which will come after all the non-generation stuff. Um, and as you can guess, this gets like really, really repetitive because you're basically just solving the same equation over and over and over and over and over again, just for different geometries and different boundary conditions. So all of that is done for you in the book. I'm going to just solve a few kind of examples. And if you're really interested in like solving every single one, you can find those in the book. But once I give you sort of the general solution process, you should be able to apply that to all of the different geometries and all the different parameters that we're looking for. The other thing that I'll mention is that there's something called critical radius. I'm not going to talk an enormous amount about critical radius because critical radius is on the quiz. And part of what I want you to do on the quiz is figure out what in the heck critical radius is. So I will mention that it's here, right? There's an equation for critical radius for cylinders and for spheres. I'm not going to show you where the equation comes from. That derivation is given in the book. Just be aware that this is a thing. It's important, especially for circular, right? So polar coordinates and spherical coordinates, those types of geometries. And you should learn about it when you solve the quiz. So I'm not going to talk about it here, but just in case you need the equations, they're here. Okay, so let's jump into it. Okay, so this is like the overarching standard approach to solving these conduction problems. So we're going to go all the way back to the heat equation. This one happens to be the one in Cartesian coordinates, XYZ coordinates. And you remember in the previous lectures, we essentially explained where all these terms came from. And, I didn't do the derivation. You can find that in the book, but, it basically gave the background for where this equation comes from. And then I went through and showed you all of the simplifications. So situation where you're in steady state, you have no thermal energy storage, this term goes away. If you have no internal generation, this term goes away. If you have constant properties like constant thermal conductivity in the XYZ directions, these Ks come out. They're no longer functions of XYZ, so they come out as constants. And then a lot of times, if you've got nothing on the right-hand side of the equation, they just will divide out and go away, right? So I basically showed you how to get to these three principal equations, which are the most common kind of specific forms of the heat equation. So Laplace equation, Poisson's equation, and the diffusion equation, also called Fokker-Planck. And so you should already know how to get to those equations from the heat equation. And what we're going to do now is solve at least the first two of these equations for one-dimensional conduction, right? So that's basically where we're going, is solving these guys for the temperature field and for the heat flux for one-dimensional conduction. This one we are going to solve later. There's a time derivative here, and so we have to worry about non-steady state situations to solve this one. So non-steady state stuff that's like next week. We'll get to that. And then just as a reminder, Fourier's equation is here, right? So the goal typically is to solve these guys to get the temperature field and then take the derivative of the temperature field and plug it into Fourier's equation and out pops the heat flux. And so you know how hot everything is and where the heat is going in your object. So that's kind of the big goal. So the solution process that I'm going to walk through it, for a couple times, and then everyone's going to get bored, right? So I'm not going to do it more than two or three times. But it follows these kind of three process steps. So first, we're going to obtain the general temperature distribution by solving the appropriate form of the heat equation, right? So we're going to take the appropriate form of one of these equations and we're going to solve it for the temperature field. we're going to end up with an equation that has a number of constants in it. And those constants we don't know, right? Because we got those constants from an integration process. And so we're going to need to apply the boundary conditions to pin down the values of those constants. So that gives us a so-called particular solution for our specific problem with the boundary conditions set the way that they are. And then once we have that temperature field with all the constants pinned down from the boundary conditions, then we're going to take that particular solution for the temperature field and we're going to plug it into Fourier's equation or Fourier's law to determine the heat transfer rate, right? So that's kind of the overall scheme that I'm going to follow over and over and over again. Okay, and what I will say before I go on to the next slide is this process is like really onerous. And so just like with everything in engineering, right, once you kind of get the gist of it, right, once you kind of understand the steps and the cadence, there's all kinds of shortcuts. And so we're basically going to do this like once or twice. And then I'm going to say, look, here's the shortcuts. And from here on out, just use the shortcuts. Because if you had to actually do this from scratch for every single problem, you'd never finish, right? Like you'd be solving heat transfer problems until you retired. So the shortcuts speed things up quite significantly. Things like 1D resistor model and stuff. So we'll talk about, how that gets applied once you know how this works. The shortcuts will be quite helpful. So the easiest place to start is 1D conduction through a plane wall, right? So this is Euclidean geometry, XYZ geometry, but of course we only have one dimension, so it's X geometry. And what we have here is just a plane wall, and there's a coordinate system. So X equals 0 is kind of the far left side of the wall, and then the wall has a thickness of L. So at X equals L, you're on the other side of the wall. And this wall has got two convective boundary conditions that basically set the temperature on either side of the wall. So we've got hot fluid kind of blowing here up and down the left side of the wall, and we've got cold fluid blowing up and down the right side of the wall, and some free stream temperature on the hot side and free stream temperature on the cold side, far away from the wall. And those two convection processes basically set the temperature of the surface at X equals 0 and X equals L. And because you have a temperature gradient, right? Remember the definition of heat transfer. Anytime you have temperature gradient, you have transfer of heat. So there is some conduction of heat through this wall. And this is one dimensional, right? So there's no heat up and down. There's no heat into the screen or out of the screen. It's just from left to right. So that's this heat term here. Okay, so that sort of covers the underlying assumptions. One dimensional, steady state, right? So these temperatures are fixed, they're not changing with time. No energy storage, no internal energy generation, right? So I'm not storing any energy in here. I'm not spontaneously generating any energy, right? Which might seem very weird, but you can generate thermal energy by taking energy of another form and converting it into thermal energy inside one of these plane walls. We'll actually get to that later. There's a whole section in this chapter on having a non-zero generation term. But you could, for example, run like current through a metal wall, right? And it would dissipate thermal energy as Joule heating. And so that's what we mean by no internal generation. There's no like internal heating in the wall, and then constant thermal conductivity. Okay, so with these assumptions and this setup, the thermal energy equation, this monster here, right, thermal energy equation, simplifies into Laplace's equation. Yay, Laplace's equation, right, where just the second spatial derivative of temperature is equal to 0. I have intentionally, at least for now, I know I say right here, constant K. I've left the thermal conductivity in here, and you'll see why in a second. It does eventually come out, and I'll point out to you when it does, but I want to leave it in here just to kind of give you a bigger picture, right? Just for completeness. So don't worry about the K sitting in there right now. It will eventually come out of the derivative, and then it'll just get divided away. But for now, I'm gonna just leave it in there. Okay, so we have two boundary conditions. So the first one is that at X equals 0, the temperature is TS1, temperature of surface 1, right? So that's right here, X equals 0, TS1. And then here we have at X equals L, the temperature is TS2, surface temperature 2, right? So here's X equals L. Here's temperature surface 2. Okay, so those are our boundary conditions, right? And remember, we have to have two boundary conditions because we're talking about second derivatives, second spatial derivatives. So for every like order increase of your differential equation, you need an extra boundary condition to pin things down. So second derivative implies two boundary conditions. Okay, we got that. And now we're going to integrate twice. So this is that moment where k is sitting in here, and now I've taken k out as a constant, and I've divided it out, and so that's where k goes. It seems sort of silly and trivial here, but later on when we talk about radial coordinates, leaving the k in there, at least for this step, will turn out to be important. So I wanted you to like see me do it in a situation where it doesn't matter. And then we'll see later on why it does matter for radial coordinates. Okay, so we're going to do two integrations. So here's my first integration, right? So derivative of dt dx is equal to the integral, or I should say integral of dt dx is equal to the integral of, remember this was just a 0 dx, right? Where did that come from, right? 0, 0 dx, right? Okay, and so I do this integration, and what pops out is this thing sitting inside my integrand comes out. So here's dt dx, and that just equals a constant, right? So constant of integration that comes out of this guy. I'm basically taking the integral of 0, so I get a constant. So that's where my first constant comes from. And then I want to take another derivative. And so here I am doing that, right? So here I'm integrating. Oh, sorry. I want to not take another derivative, take another integral. There we go. So here I am taking an integral, right? So here's the derivative of t, taking integral. And then here I am taking the integral the other side. So this dx moves to the other side of the equation. So integral of c dx. And what comes out is some temperature as a function of x is equal to c1x, right? So here's the c1, and here's the dx, which is integrated to x, and then plus another constant of integration. So I end up with this expression, which is that t as a function of x is equal to some constant times x plus some other constant. It's just a line, right? The equation of a straight line. So not maybe enormously surprising, given that I've already drawn a straight line here for you. So that's what it looks like. It's just a line. Okay, so now in order to pin down these constants, I've got to put in my boundary conditions. So the first boundary condition was at x equals 0, the temperature is the surface temperature of 1. So I plug that in here, right? So surface temperature of 1 is equal to C1 times 0 plus C2, right? So here's the 0 for x. And that gives me that C2 is just equal to the surface temperature at location 1. And then I plug in my other boundary condition, x at L is T surface 2, right? So here I'm doing it, right? So I plug in C1 times L plus C2, right? C1 times L plus, okay. And then remember C2 is surface 1. And so out pops the expression for C1, which is just T surface 2 minus T surface 1 divided by L. Okay, so now I have C1 and C2, so I take those values, plug them back into here, and out pops this equation, which, as I said, is just the equation of a line, right? So it's got a slope of TS2 minus TS1 divided by L, and then it starts at some temperature, which is TS1, right? So it starts at TS1 and the slope just poop, goes down. Okay. So now that I have my temperature field, I could take this guy and I could plug it into Fourier's law. So remember, this is Fourier's law, right? So I want to take the first derivative of this guy, dt dx, plug it in here, minus ka dt dx is equal to q. So I take the derivative of this guy with respect to x, I get ts2 minus ts1 over L, and then I multiply by minus ka, and there it is, boom. And if I want a so this is a rate of heat transfer. If I want a heat flux, which is rate of heat transfer per unit area, I just divide both sides by area. And so that's what this little double prime means. This is a heat transfer per unit area or heat flux. And that's just the heat transfer divided by the area. And of course, the area disappears from my Ka side of the equation, right? So, okay. So these are my kind of big take-home equations, the temperature field, the heat, and the heat flux. Okay, so I say here, takeaway for plane wall conduction. One is that the temperature varies linearly with x. So we said that this is just the equation of a line. And the other thing, which is kind of fascinating, is that the heat flux is independent of x, right? So nowhere in this equation is there an x. In fact, given that TS1 and TS2 and K and L are constant, this heat flux is constant, right? Not a function of x, but a constant value. So that's pretty cool. Okay, now we've walked through that process, and remember what we did. Remember what we did is we started from here and we walked through these three steps. And you can imagine how onerous this would be if you had to do it every single time. So we introduced something called the electrical resistance analogy, which works for all three heat transfer modes: conduction, convection, radiation. And we're going to use this kind of as a shortcut, if you will, so that you don't have to do that every single time. Anytime you're in one-dimensional, steady state, not changing thermal properties, all the assumptions that we made, you could use the electrical resistance analogy and get the correct answer. So if you remember all the way back to your circuits class, this is, I actually love this cartoon because it, I think, really illustrates what's going on. Think about electricity, right? So you have voltage, which is kind of this yellow person who is pushing current, which is this green person down a wire. And then there's this red person representing resistance, and that resistance is trying to stop the current from flowing, where the voltage is trying to entice the current to flow. And so there's, kind of this um, relationship between these three: voltage, current, and resistance, which is embodied by this equation, which is that current is equal to voltage divided by resistance. Um, Okay, and if you remember back from baby circuits, or well, we're not allowed to call it that anymore, from your circuits class that was very rigorous, um, you have a bunch of tricks for how to handle resistances, right? You remember resistances in series, resistances in parallel, like you know how to manage resistances and how they all stack up with each other. And so that's the direction that we're going. We're going to actually start building up electrical circuits that are analogous to thermal circuits, and we're going to solve them using all the same rules that you use to solve the electrical circuits. And then the result will be basically a heat flux and a temperature field that comes out of it. So you can see the analogy here, right? So current, which is the electrons flowing through the wire, is analogous to my heat transfer, right? So this is thermal energy flowing through, whatever it is that I'm modeling. This is my voltage, which is the potential difference, the yellow guy like pushing the heat along in the one-dimensional heat transfer process. And so that's analogous to my temperature difference, right? So I have low temperature and high temperature, and the high temperature is like pushing the heat towards the low temperature, right? So that's where that analogy from voltage comes from. And then I have some resistance, right? So the yellow guy, who's basically trying to impede that flow of thermal energy, that flow of heat, the same way that a resistor in a electrical circuit would impede the flow of electrons. And so I have this resistance term, and that's analogous to Ka over L in my Fourier equation. Okay, so what I want to do then, because I want to get into that world where I can use everything that I know from electrical engineering to model these one-dimensional heat transfer processes. So I want to write something that looks like a resistance, so I can then use that resistances in series, resistances in parallel, all those equations to get my temperatures and my heat fluxes. So I say here, for one-dimensional heat transfer with no internal energy generation and constant properties, I can write this thing called R sub T cond. So T is thermal and cond is conduction. And this is just, I'm just taking this guy and I'm just dividing both sides by the temperature difference, right? So here's temperature difference over Q. And then what's left over is just L over Ka. And that is my heat transfer thermal conductivity, right? And it turns out this is perfectly analogous to what we find in the electrical world, right? So here is my R sub T. I said that T was thermal before. Hmm. This is not thermal anymore. Okay, I'm going to check on what T means. It might mean something else. Um, hmm. Anyway, this is my electrical resistance, and I've got my potential difference, right? So this term, this difference is just two voltage potential differences, right? So you subtract them, you get V divided by current, and that is equal to the length of whatever it is that you're conducting current through, divided by its electrical resistivity and its area, right? So this term and this term are perfectly analogous to each other, the same way that this resistance term for thermal conductivity and this resistance term for, sorry, this resistance term for, yeah, for thermal conduction and this resistance term for electrical conduction or electrical resistance are analogous. Okay, so, whoops, uh-oh, there we go. Okay, so we've done it for conduction. We also have convection and we have radiation, right? So once you've done it for conduction, it's like, gosh, if I have a situation where I've got some sort of convective or some sort of irradiative like boundary condition, like I can't use any of my resistance tools from circuits anymore. This is really bad. So we just said, okay, we're going to make convection and radiation look exactly the same way. So same exact analogy. Current is equal to voltage divided by resistance. This is Newton's law of cooling, my convection equation. This is, if you remember from the first lecture, this is the equation for radiation, where we basically take um, this guy, and there's a lot of complexity in here, but it basically breaks down into just the equivalent of a convective heat transfer coefficient, but sub R for radiation. And hey, these start to look an awful lot like conduction, right? I've got Q is equal to HA delta T, and Q for radiation is equal to HA delta T. I've got a delta T, which is like a voltage. I've got a Q, which is like a current. And then this HA thing takes the place of resistance. And so I can do exactly the same thing that I did before for conduction, but now I'm doing it for convection and, this should say radiation, for convection and radiation. Um, and I'm just saying, okay, I'm going to have a resistance for convection, and that's just my temperature difference divided by Q, which is 1 over HA. And I'm going to also have it for radiation. I'll change this in the final slides. Temperature difference divided by Q, that's just equal to 1 over H sub RA. And so I've now got expressions for the equivalent thermal resistance for conduction, which was the previous slide, and then convection and radiation here. So I can now, voila, write thermal circuits using this resistance analogy where this guy is like a convection, right? So 1 over HA is a convection, and this guy, L over KA, that's a conduction. And if I've got processes where I've got like a convection and then a conduction and a convection, and those are happening kind of in series, then I can actually just write the equivalent series resistances, and I can use all of my circuits resistance equations to figure out what the total resistance of this thing is. And then I know that the potential that's driving the heat across this set of resistances is just the temperature difference. And so I can use that to back out the heat transfer. So that's what I'm doing here, right? So I've just added to that previous plot that I showed before this kind of green heat flux term, or heat transfer term. And then I'm showing here that because this term, remember, not a function of x, right? It's constant all the way through. So any heat that enters at this spot has to travel through here and has to leave at this spot. And so that heat flux from T infinity to TS1 is the same as from TS1 to TS2 is the same as from TS2 to T infinity 2, right? And so that's all I'm writing here, that these heat fluxes are all the same. And what are the heat fluxes? Well, it's just the temperature difference divided by the equivalent thermal resistance for each of those situations. So this one is the convective resistance out here. This one is the conductive resistance in here. And this one is the convective resistance over here on the far right-hand side. And if I wanted now to say, okay, I want to actually figure out the heat transfer from way out here where it's hot at T infinity 1 all the way over here to where it's cold at T infinity 2. Well, I can do that too. All I have to do is just add up these series resistors, right? So that's what I'm showing here. I've just got these three resistances, convection, conduction, convection again, and I'm just adding them up, and this heat flux or heat transfer just goes through, right? Here it is here on the actual drawing, and then here it is here on the circuit schematic, so it's just going through. And I'm just going to write that Qx is equal to the temperature out here minus the temperature down here divided by some total resistance. So our total. And what's our total? Well, I know because I took a circuits class that it's just the sum of these three resistances in series. So here I'm just going to add them up. Boom, 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 three resistances in series. And that's it, right? So now I can take this guy and I can plug it in here and I can solve for what this Q is based on these resistances and these temperatures without actually needing to know any of the internal temperatures. And oh, by the way, if I wanted to know the internal temperatures, I can then take this heat flux that I've already solved for, plug it in up here, and then solve for the temperature at this spot or the temperature at this spot using this equation, right? So just like all of the tools that you guys have from circuits, it's perfectly analogous to use them here. So let's see, what do I say here? The circuit representations are useful to conceptualize and quantify heat transfer problems. Heat transfer rate is determined from separate consideration for each element of the network, right? So that's just restating what I was saying here, right? That once you know what the heat flux is, you can find the heat flux through each of the individual thermal resistances, which allows you to find surface temperatures that you wouldn't be able to find otherwise unless you had these equations. Okay, so let's move on. All right, so now that we've got this circuit analogy, we can start using it to make more complicated models um, for more complex thermal systems. So this is a composite wall, so called because I have three different materials in here that are all stacked together, and each one of these could conceivably have a different K value, different thermal conductance, right? So a lot of things in the real world look like this. If you're building like a building, for example, you've got let's see, this is hot, so and this is Florida, so this is going to be like the outside, right, is hot, the outside wall of your house, the insulation of your house, the inside wall of your house, and then the inside of your house, right? So that's just one example of like how a composite wall would actually be structured in the real world. So we could use the exact same circuit analogy. We just add more resistors, right? So remember, I've got this equation that just says that my heat transfer rate is equal to the high temperature out here minus the low temperature down here divided by some sum of resistances. And what are those resistances? Well, like look here, right? They're just the resistances associated with convection out here, conduction through element A, conduction through element B, conduction through element C, right? So here's the resistances for A and B and C. And notice the form is the same, right? L sub A over K sub A times A, right? Same thing. Um, and then finally, I've got the convection out here, 1 over H, looks like H4A. So each one of those is its own separate resistance. I just sum them up, and that gives me the total resistance that I can plug into this equation, right? So here I am just showing each of these individual resistances and that you sum them up to put them in the denominator here. And then there's this area in all of these terms. And so when I put them in this form, this is just the distributive law of multiplication. I'm pulling out that area. And that gives me kind of a different expression for this, which is the overall heat transfer coefficient. So the overall heat transfer coefficient is just if I take this A and I multiply both sides by A, and then I invert the whole thing, right? I flip it over. I get this thing called U, which is the overall heat transfer coefficient, which is just 1 divided by each one of these resistances, but without the associated area, right? Because the area is the same for all of these, right? It's the cross-sectional area into the page, essentially. And that's just sitting here, right? So I get this U value. And then the ultimate goal here is to write my heat transfer rate is equal to U times A times delta T. Delta T is the temperature difference. A is the area, right? All these areas again are the same, so I can pull that area out. And then this U thing is my overall heat transfer coefficient. It's the same as a heat transfer resistance. It's just it shows up in the numerator instead of it's in the denominator. And the reason that I'm interested in this form of the equation is because this looks an awful lot like Newton's law of cooling, right? Which is just a Q times an HA times a delta T. And we're not going to use this extensively now, but I want to show you this because when we get into heat exchangers, this U value becomes quite important, right? You're going to end up, when you design heat exchangers, like building up U values from convective and conductive heat transfer resistances. So I want to just show you this now. You end up with Newton's law of cooling. Um, Okay, so that's just, adding up a series of resistors in a composite wall. So that should feel relatively comfortable and familiar because you guys have done this a whole bunch of times in circuits. Okay, so now a little bit more complicated. You could also have a composite wall that has different sub-elements in it, right? So just like the previous wall, I have these layers that are kind of continuous all the way through, and then I have these units F and G, where F can have potentially a different thermal conductivity than G does, and they kind of split the heat transfer between them. And if you start imagining, what this actually looks like, it starts to look like two resistors in parallel, right? You've got a heat transfer path that goes this way, and you've got a heat transfer path that goes this way. And so you can imagine kind of um, a parallel analogy here as opposed to a series analogy like we did before. Just in case you don't remember the equations for how to treat resistors in parallel and resistors in series, I went into an electrical engineering website and grabbed these schematics. And so remember, 1 over the equivalent resistance for parallel resistors is just 1 over R1 plus 1 over R2. And then you have resistors in series, the equivalent resistance, you just sum them up, right? Just like we did here. We're just summing them up, right? So, but if you're in this situation, you have resistors in parallel, this is how you handle them, right? So 1 over equivalent plus 1 over R1 plus 1 over R2. Okay, so here's where things get a little weird. Um, we have assumed one-dimensional heat transfer. And what that means is if I imagine these things as resistors in parallel, um, I've got a constant temperature here and a constant temperature here, and then two separate heat paths, right? So that's this thermal circuit. Another way of thinking about it is I can just divide this. So I can cut a line all the way through here, and I can start with this temperature and make these two separate paths where there's no heat transfer from one path to the other. They're essentially isolated from each other. So let me show you what that looks like. I have, well, here, before I show you that, let me just make sure I read through this. Okay. So I say sometimes it's reasonable to assume 1D conduction. Okay. So what I was about to say, which we'll see on the next slide, is if one of these has a higher thermal conductivity than the other one, the heat will travel through the higher thermal conductivity more readily, and the temperature here will go up. And then you're going to have this interface here where this guy is hot and this guy is cold, and we are like artificially barring the heat from moving from the hot side to the cold side. So that's why I say here sometimes it's reasonable to assume 1D conduction, right? In that we're making that 1D conduction assumption in this kind of series parallel configuration for composite wall, recognizing that we're not allowing a heat transfer path from, say, the hotter member to the colder member. So I say here, two different possible thermal circuits result. We have surfaces normal to the x direction or isothermal, right? So that's what I described. We have constant temperature here, 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 here. So those are all isothermal surfaces. That's one extreme that gives us this circuit model, right? So constant temperature here, 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 and here. And then the other extreme is the surfaces parallel to the x direction are adiabatic, right? So this is what I described before, where we've got basically a line here where no heat can cross, and that's this circuit. Right, so we allow the heat to enter. We have a constant temperature on this far surface, and then the heat takes one of two paths, and it's not allowed to conduct even in this member, which is a uniform member all the way across. It's not allowed to conduct from this top side, which could be hot, to this bottom side, which could be cold. So these two different circuit configurations result in a different value of R total, and then correspond to a different heat transfer rate depending on which one of these configurations you choose. And it turns out that what I've just described are the two extremes that bracket what actually happens. So this is a technique that's often used, at least as kind of an initial guess, when you have a series parallel configuration like this. You'll set up this configuration and solve for Q. You'll set up this configuration and solve for Q, and the actual answer is bounded between those. And sometimes they're very close to each other, and so you get an answer that's good enough for engineering purposes. But as I say here, the differences between these two extremes, these two bounding extremes, do increase with increasing multidimensional effects. So by multidimensional effects, I mean like this guy gets really hot, this guy stays cold, and you're not allowing the heat to transfer from the hot side to the cold side in a second direction. Once those effects get big, the differences between this configuration, that configuration get very large. So this, in some cases can be helpful to approximate Q. In some cases, if those temperature gradients are really big, not super helpful. Okay, so this is just a visual representation of what I was showing before, right? So we've got our same thermal circuits here, and we have, so if we go back, remember, we've got surfaces normal to the x direction or isothermal. So I'm showing lines of constant temperature. There's one here, there's one here, that's the yellow dotted line, there's one here, and then there's one here. And the heat travels through member E, reaches the barrier of member E, provides a constant temperature surface here, isothermal surface here, and then breaks up into two parallel heat transfer paths that then terminate in constant temperature here as they emerge into H. And then there's just one heat transfer path all the way through H, right? So that's this guy. As I said before, there's an adiabatic separation, right? So a non-heat transfer separation between F and G. That's this purple line. So heat's not transferring from here to here, even though one of these could be hotter than the other one. In the other extreme, we're just cutting this thing right in half, right? So here's my purple adiabatic line. And I'm going to say, okay, it's constant temperature here at T1, constant temperature here at T2, and I'm not going to let any heat transfer between the top side and the bottom side, QX1 and QX2, as soon as it's traversed into E, right? It's just going to travel all the way through without any heat transfer. And so that's this circuit analogy here. So this is the one where we have surfaces parallel to the x direction or adiabatic, right? So here's parallel to the x direction, and here's a surface that's adiabatic, and that adiabatic surface gets extended across member E and member H, even though those are monolithic, uniform. Okay, so those are the two extremes. What does this thing actually look like in reality? Well, I jumped into AI and I had it solve the actual two-dimensional heat transfer equation for this configuration, and this is what it came up with. So notice that the isotherms are continuous curves through all members, right? So isotherms are lines of constant temperature. Remember here, we artificially imposed two isotherms on these boundaries, and in the real situation, those are not there, right? So here's maybe the closest isotherm, and it crosses over like that, and here's the closest isotherm on the other side, and it crosses over. So those lines of constant temperature are not just perfectly vertical in the real two-dimensional situation. Also, member walls do not impede heat flux, right? So you can see here, there's a very uniform temperature gradient between this top member and this bottom member, and that's because we're allowing heat to travel through this surface, whereas up here, it was not allowed to travel through here, and it was not allowed to travel through here, right? It's not true in this case. So the heat can actually go through. So what I'll leave you with is just a question for you to answer on your own. This top one is F, this bottom one is G. Just looking at this plot, can you figure out which one has a higher thermal conductivity? Which one is more amenable to allowing heat to transfer through it? And I won't answer that question. I'll leave it for you guys to figure out. But hopefully, having just talked through this, it should be clear which one of these has a higher K and which one has a lower K. Based on the temperature profiles and the heat fluxes that you can see in this heat map. Okay, what's this? Whoa, getting ahead of ourselves. Okay, so all I wanted to show here was just so I was meant to go from this slide to this slide and just show that the heat fluxes and the isotherms and the adiabats that I'm showing here in the schematic also appear in the circuit diagram, right? So if we look, right, so heat flux, constant temperature, heat flux, constant temperature, heat flux, and boom, that's exactly what happens, right? And then here, same story. We have heat flux, adiabatic line, heat flux, and then here, boom, heat flux through the resistors, adiabatic line, heat flux through the resistors on the bottom, right? So just to point out that what you're seeing in the physical composite wall is analogous to what you're representing in the circuit in terms of the heat fluxes, the isotherms, and the adiabatic lines. Okay. Now, you guys saw kind of a goofy slide for a second there, which I didn't mean to show you, but I want to take just kind of a quick detour into the world of AI frustration. Um, I mentioned that I used AI to generate this figure. You should always, whenever you use AI, obviously attribute it, right? So I'm letting you know I used AI to generate this figure. Um, but man, what a nightmare this was. So, and this is why, right, it's important for you guys to like use AI and develop that skill set. All engineers in the future, I think, are going to need to use AI at various aspects of their professional practice. So it's an important skill set for you guys to build up. However, you have to do your own thinking. You cannot just tell AI to do it for you and just trust what pops out. So I had to iterate on this thing for about 30 minutes to get the right answer. Right. So here's my Captain Picard facepalm. And I said, okay, right. So I fed basically this configuration into AI. And I said, okay, one of these members has a higher thermal conductivity than the other. Give me the temperature field. And AI is like, okay, I'll give you the temperature field. And so first it did this, right? Which actually is pretty good, right? Not great, but reasonably good. The isotherms at least are continuous and they're at least, are vertical, right? So pretty good. But it did not change the background heat map, right? So if you look at the heat map, the heat map is one dimensional, right? It just changes as you march forward in the X direction, and it doesn't show any kind of Y direction deviations, right? So that's not right. So then I said, okay, it's time for you, AI, to change the heat map so that it matches with the isotherms. And A is like, okay, I'll do that. And this is what it spat out, right? So, oh my God, things are getting worse, right? So it didn't actually fix the incorrect heat map. And then it started doing this goofy thing with the isotherms where they like connect to each other, but they all get drawn towards this corner. And I have no idea what the hell's going on here, but that's not what isotherms look like, right? And then you've got this sort of like orphan one right here that's not attached to anything, and an orphan one here that's not attached to anything. So things are just getting worse and worse, right? So I pointed out the problems there to AI, and it's like, okay, I'll do it again for you. And then it gave me this. I'm like, oh my God, it's just getting worse. So in this case, it made the isotherms, these are lines of constant temperature, like parallel to the heat flow instead of perpendicular to the heat flow, which is totally wrong, right? Because flux and temperature have to be like 90 degrees from each other, right? Perpendicular to each other. So that's totally wrong. And then it has like a fixation on this corner, right? It drew all of these isotherms into this corner. It made this whole thing red. It's like, oh my God, what in the hell is going on with this? So I just had to start over again. I actually opened up a completely different AI agent and fed it like a completely different set of prompts and was able to basically work my way through a solution to the two-dimensional heat transfer equation to get this figure out of it, right? But wow, this was a pain in the butt. So I just wanted to show you guys this, right? This has nothing to do with heat transfer, but it's important for you as engineers in 2026 and beyond to recognize that AI is a very important tool, but it's going to hallucinate, it's going to lie, it's going to make up all kinds of stuff that's basically wrong, and you have to know enough to be able to critique it and know that you're getting answers that are crap. And you have to be able to like fight it into submission to get the answer that you know is correct based on your engineering knowledge and intuition, right? So I knew, from the get-go when I was looking at the isotherms getting worse and worse and worse that the AI was hallucinating. So anyway, that's my AI rant for this lecture. Let's move on to porous media. Okay, so now that we have this composite wall um, knowledge, right, and this ability to say, okay, I can draw or create resistances in series and resistances in parallel, and those represent kind of bounding situations for real composite objects. I can take that knowledge and I can extend it to other things like porous media. So porous media. And typically we're talking about insulators. So I say here, insulators are often porous and they're combinations of a stationary solid and a stationary fluid. The word stationary is very important. There's a whole section later on in the class we're going to talk about packed beds. Packed beds are situations where the solid moves and the fluid moves, right? So porous media and packed beds, two different things. Right now we're just talking about porous media where everything is basically stationary. So you can basically use the steady state heat flux equation to write a temperature heat flux relationship for heat transfer through porous media with kind of the caveat that there's this thing called K effective, which is sitting there, right? It's an effective thermal conductivity. And the question is, how in the hell do we get K effective? So I say here, K effective is the effective thermal conductivity. It's a function of the void fraction. This is, I think, epsilon, and thermal conductivities of each phase. Here, I'm going to give you equations that assume that the thermal conductivity of the solid is much higher than the thermal conductivity of the encapsulated fluid. So we are talking about something like an insulator, right? Where you've got some solid and it has captured some gas inside of it, and you're using it to try to reduce the rate of heat transfer. So for example, like batting in a building, right, or styrofoam in a packing container, qualifies as something where the solid has a higher thermal conductivity than the encapsulated fluid. Okay, so this void fraction is defined as the volume of the fluid divided by the total volume. So volume of the fluid plus volume of the solid. So that ratio gives you the void fraction. And we can play the same game that we played before with these thermal circuits, right? So series parallel heat transfer paths that bracket the actual value of K effective by modeling the porous media as a series or parallel composite wall. So we'll start out by modeling it as a series composite wall with the fluid region length equal to epsilon L, and then the solid region equal to 1 minus epsilon L, right? So I show that here. So we have this is going to be the solid region, right? So however much material I have that's solid, I'm going to represent that as 1 minus epsilon L, and I'm going to take the thermal conductivity for the solid, and I'm going to assign that to this first resistance in my series circuit. And then here, this is the fluid, right? So this is just epsilon L in terms of its length in the resistance. And I'm going to use the thermal conductivity for the fluid. I'm going to plug that into this resistor here, and that's going to give me a minimum value of K effective. Um, the maximum value of K effective comes from putting things in parallel, right? So I'm now um, talking about, instead of the length of these pathways, I'm talking about the width of these pathways. And here is the pathway for the solid, and here is the pathway for the fluid. And the widths of those are 1 minus epsilon times W, where W is the entire width of this composite object. And then epsilon W, right, is just that's the fluid portion of it. And this guy just creates two parallel paths. And so that can be represented as two resistances in parallel. And that gives me the maximum K effectiveness, right? So just like before with the composite wall, if I calculate the minimum K effectiveness, I'm going to use my equation for resistances in series, which is here. And then if I'm trying to find the maximum K effectiveness, I'm going to use my equation for resistances in parallel, which is here. Notice, right, this seems a little weird, right, because these are added together, right? And these are like added together in the denominator. But notice we're talking about not resistances, but thermal conductances. So I'm using the equations that are given in the book. So that's why this looks a little weird. They're not actually resistances. They're 1 over resistance. They're conductances. But same idea. So I'm adding them up here because these guys are in parallel. So I'm basically adding two heat transfer paths. And then here I'm treating them in the denominator because they're two heat transfer paths that are in series with each other, right? So that's why these guys are reversed, conductances instead of resistances. The book also gives I'll use the word ballpark estimate for K effective, which is true for void fractions less than or equal to about 0.25, so 25%. And what it says is that, I'm not even going to try to read this. K effective is this guy divided by this guy multiplied by the thermal conductivity of the solid phase. So by the way, F is for fluid and S is for solid, if I didn't mention that before. So this is an equation out of the book that you can use. Again, gives you a ballpark estimate for K effective. If you find that the minimum and the maximum are so far apart and you need a value that kind of splits them, this is what the book recommends to use for this. Okay. So while we are talking about this resistance analogy in heat transfer, the analogy between electrical resistance and thermal resistance, another resistance that I want to mention is called contact resistance. You guys are going to battle this one quite a bit. I think in the heat transfer lab kits, because it'll rear its ugly head at least a few times. But this is a resistance that shows up owing to the surface roughness between two solids that are in physical and thermal contact with each other. And kind of on the macro scale, if you look at two objects that are in contact with each other, their surfaces are smooth. There's, just perfect conductivity, perfect heat transfer from A to B. But if you zoom in, what is actually happening is there's some roughness on these surfaces, and those roughness areas create kind of patches of fluid, usually air, and then little locations where there's actual physical contact between the material of A and the material of B. And you can sort of get a sense when I talk about surface roughness. I've just got an image here from like a machinist website that just shows various different finishes and the surface roughnesses, which are visible based on this different manufacturing process. I think these are just different sandcast processes, and this one might be machined. But you can see, like, imagine two surfaces that look like this that are butting up against each other, right? There's going to be an enormous amount of like air in between those two surfaces, and that air impedes the heat transfer from A to B. And so therefore, in our resistance analogy that we've been talking about this whole time, behaves like another resistance. And so what I want to point out, I've actually got it circled here in purple to remember to talk about it. The thermal gradient is coming in, right? So here's the temperature profile linear, right? Because it's one dimensional conduction through a slab with no generation, right? So we've seen that before. So here it comes in, it's linear, and then it gets to this interface, and all of a sudden it skips, right? It jumps. So jump in temperature, and then it resumes some other lower temperature, which is temperature B in this case, and then it continues on as a straight linear temperature profile until it reaches the edge here, right? So this kind of jump in temperature across interfaces is what characterizes contact resistance. And we will see this again when we solve the example problems. Okay, so I say here, surface roughness creates thermal contact resistance. Contact spots are interspersed with air-filled gaps, so the heat transfers across the contact spots and it is impeded from transferring across the gap, although there is a representation here of a little bit of heat transfer across the gap. So this is either conduction in the gas or sometimes radiation between A and B across that void. And I say contact area is typically small. And so the major resistance to heat transfer from A to B is contributed by the gaps, right? So these gaps. And so the bigger the gaps, right? So the more kind of air you have in there, the bigger this contact resistance gets. And then here's our equation for it, right? So just like the previous equations, where did I do it? Right. So like right here, right, where I'm basically just writing, or I think I did it. Yeah, here, where I'm writing a temperature difference divided by a heat flux to define what that resistance is. We're going to do the same thing here, right? So temperature divided by a heat flux gives us this resistance. Okay, so that's the value. Typically, these values are empirical. There are some models to predict them, but the models are not very good. And so usually these values will actually be measured. And then you will plug them into this equation and either solve for your temperature difference or your heat flux, given that you know two things and you're trying to solve for the third thing. So just to give you some kind of order of magnitude sense of what these thermal resistances look like. These are all the same material, right? So lapped silicon chip. Let's see, silicon chip. Oh, okay. No, I'm wrong. I thought they were, many of them are the same, right? So we've got aluminum, 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 stainless, stainless. This one is different. So we've got a silicon chip and lapped aluminum and air. And we have a thermal resistance of 0.3 to 0.6 times 10 to the fourth watt squared times Kelvin per watt. Let me try again. Blah, blah, blah. Meter squared, Kelvin per watt. There we go. Okay. And then you look at other, so here's like two stainless steel surfaces with a layer of indium foil. So indium is a metal that basically liquefies right above room temperature. And it's highly conductive. It'll fill in all these little gaps, right? So people use that to promote heat transfer. And so you can see the value there is pretty small. We have aluminum and aluminum with a lead coating between them. We have aluminum and aluminum with some sort of thermal grease. We have stainless and stainless with that same thermal grease. So you can see here, like these are just values for kind of typical situations where somebody is trying to actually reduce the contact resistance by kind of sticking something in the gap, right? So you guys are probably familiar with this from using like thermal grease on to cool down a circuit board, for example, and attaching a fin to circuit boards. Okay, so the other thing about contact resistance, which you could see it here, right? So these are pressures that are given, right? So force per unit area, force per unit area, force per unit area. Contact resistance is reduced by squishing the two surfaces together, which increases the contact area between the materials and reduces the gap, right? So that's basically what I'm showing here, right? So this is a kind of a low pressure situation where these two members are not being pushed together. And you can see there's a little bit of heat transfer between this contact point, maybe a little bit of radiation across this one and this one. But then when you push them together, when you pressurize them, you close those gaps, increase the conduction area, and the heat transfer resistance will go down as a result of that. And so one of the tricks that people do to try to reduce thermal resistance, contact resistance, is to just pressurize the two sides, right? So push them together, right? Put them in a clamp, push them together. So I say here, reduce resistance by increasing contact area, which you can either do by increasing the pressure or by reducing the roughness, right? So you can go here and you can, if you're like rough, you can lap the surface down to improve its surface roughness and get here. And if you're much more smooth, then you have a lot fewer air gaps. And so that's another way of reducing contact resistance, is reducing the surface roughness. Another thing that's done if you can't increase the pressure or reduce the surface roughness is to introduce some sort of interstitial or interfacial fluid. So you can introduce a fluid that has a large thermal conductivity. We talked previously in the gas world about helium being, sorry, not helium, hydrogen being used, because hydrogen atoms or molecules are very fast, right? And so transfer heat very fast. So a lot of times, if you're in a gas situation, hydrogen gets used. And then if you're in a situation where you can put a liquid in that interface, there's a lot of liquids that have high thermal conductivity, like oils and glycerins, that end up getting used. So what I'm showing here is more values of thermal resistance, right, in units of meters squared, Kelvin per watt. For these are the similar materials, right? This I got messed up. So we've got two stainless steel surfaces, or two copper surfaces, or two aluminum surfaces, and then at two different pressures. These are kind of typical ranges for contact resistances of a like-on-like material. And then if you put in some sort of interstitial or interfacial fluid, this is the benefit for doing that, right? So the let's see, aluminum interface, surface roughness. Yeah, with different interfacial fluids. Oh, okay. Sorry. Let me make sure I get this right. So this is just the aluminum, right? So just this last one, the aluminum interface, with a surface roughness of 10 micrometers, and a pressure of 10 to the fifth Newton per meter squared, right? I intentionally copied this so you'd have the right information, with different interfacial fluids. So you can see here, okay, this makes more sense now. You can see here, as I'm increasing the thermal conductivity from air to helium to hydrogen, I'm decreasing the thermal resistance. And this is, again, me putting either a gas or a liquid into this space between two surfaces, which are aluminum surfaces. And at 10 to the fifth, right, which is this one. Yeah. Okay. The other thing that I show here is just kind of a plot so that you can see it, right? So here's contact pressure on the x-axis, and then here's thermal contact resistance on the y-axis. And we have dotted lines for smooth surfaces. Oh, no, sorry. Dotted lines represent higher temperatures, so 150 Celsius. Constant lines are 75 Celsius. So you can see there is a temperature dependence as well. But as we increase the pressure, the contact resistance decreases. And then also, as we improve the surface roughness, the contact resistance decreases, right? So you can see all those trends: temperature, let me try again. Temperature, increased pressure, decreased surface roughness, all contributing to lowering thermal contact resistance. This happens to be aluminum 2024, but the same trend is true for most materials. Okay. That's it for the resistance analogy, at least for plane walls. We'll get back to it when we talk about cylindrical polar coordinates. But there is a little section in the book which is called alternative conduction analysis, which I just want to mention in one slide, because there is a problem in the homework that requires this method. So we can recognize that for steady state, one-dimensional, no heat generation and adiabatic boundaries, that the heat flux must be constant and independent of x, right? So we kind of mentioned this before, right? But if I've got adiabatic boundaries, so heat cannot escape from the edges of this object, um, the heat flux through this object is constant, and I can use that to my advantage to make an integration much simpler. So we'll see how that goes in a second. And there's some added power here, which is that this this condition, there we go, applies even if the cross-sectional area is changing and even if the thermal conductivity is changing as a function of temperature, right? So you could end up using this technique for situations where cross-sectional area changes, temperature changes, K changes, and end up getting a value even though you've got kind of these more complicated geometries and heat dependent thermal conductivities. So specific to these conditions, we're going to integrate Fourier's law despite neither the heat transfer rate nor the temperature distribution being known, right? So here's Fourier's law, right? We don't know the conduction and we don't know the temperature distribution, but we know that this value is constant. And so we're going to use that to our advantage to make the integration easier. So all I'm going to do here is I'm going to take a, which is a function of x, and dx, and I'm going to move those to the other side of the equation, and then I'm going to integrate. And I'm going to integrate from x equals 0, which is just, some arbitrary spot, right, my origin. And then I'm just going to integrate out into the x direction, right? I could integrate all the way to x sub 1 if I wanted to, the far end of this thing, but I can basically integrate anywhere I want inside of it. And then on the other side of the equation, what's left is k as a function of temperature and then dt. And so I'm going to integrate from the temperature at whatever this spot is, right? That's my boundary condition, out to that same spot where I was integrating x to, and there'll just be some temperature there. And um, what I end up with, I don't know, right, for this example, what a sub x and k sub t are, but what I'll end up with, if I know a is a function of x and k is a function of t, is an equation that basically relates x to t in this geometry. Right, so this is like super powerful and super useful if you happen to find yourself in a situation where you have an adiabatic surface and like a um, changing cross-sectional area, right? So, and then there's an additional simplification, which is if A and K happen to be constants, then the expression further simplifies to basically this guy, right? So I'm just taking A and T, and no longer are they functions of X and uh, A and K. No longer are they functions of X and T directly. And this just gets me back to my conduction equation, right? So I just wanted to mention this as a technique. I wanted to show you just me doing it, at least kind of graphically, because there's a homework problem on this. So I just wanted to mention that this is a technique that you can use if you find yourself in this situation. Okay, so let's move on to one-dimensional conduction through radial geometries. So we've done the plane wall, and now we're going to do something that's cylindrical. And so remember, the same three steps that I used before is like the foundational underlying approach that I'm going to take for solving this different geometry. So I'm going to attain the general temperature distribution by solving the appropriate heat equation. Then I'm going to apply my boundary conditions to obtain the temperature distribution particular solution. And then I'm going to plug in my particular solution temperature distribution into Fourier's law to determine the heat transfer rate. And I'm going to come out with the exact same stuff that I had before, which is temperature as a function of, now instead of x, it's going to be as a function of radius, and then heat flux. And just like before, I'm going to be able to come up with a resistance analogy like I had before. The actual terms are slightly different because I'm in a polar coordinate system instead of a planar coordinate system, Euclidean coordinate system. But the same thing is true, right? I'm going to be able to write thermal resistance circuits, and I'm going to be able to solve for rates of heat transfer and temperatures inside those circuits using the exact same thermal analogy that I use for plane wall. but in now cylindrical coordinates. And by the way, I can also do this in spherical coordinates. I'm not going to show you that. Like I said, this gets really repetitive and really boring really fast, but it's in the book in case you want to see it there. Um, so I'm going to do the same thing that I did before, which is I'm going to start with my, so if we go all the way back, this is Poisson's equation, right? But it's Poisson's equation in cylindrical coordinates as opposed to in XYZ Euclidean coordinates, right? So notice a little bit of weirdness, right? This is what I mentioned in the previous lecture. I've got R, which is sitting inside this derivative. And then because the units have to work out, right? The units have to be temperature per distance squared. I've also got an R sitting in the denominator out here so that at least in terms of units, this R and this R cancel each other, right? But I end up taking this temperature derivative, multiplying it by R, and then taking this derivative with respect to R, and then dividing the whole thing by R to get to my solution. So as I mentioned before, sometimes some weirdness happens because of these R's that are kind of littered through the derivative. Okay, so we're gonna start with this. I am going to integrate this twice like I did before because I'm a second order differential equation. I need two boundary conditions, and so my boundary conditions are at r equals 1, right? So here's my geometry. I've got a hollow tube, and r equals 1 is the inner radius. So at the inner radius, the temperature is TS1, so whatever the temperature of the surface is there. And then at R2, R2, which is the outer surface, the temperature there is R surface 2, right? So those are my two boundary conditions. I also just incidentally have cold fluid blowing over this thing. So I have a convective boundary condition on the outer surface, and then I have hot fluid kind of running through the center here. And so I also have a convective boundary condition on the inner surface. Again, this is a hollow tube with, imagine it's like hot water running through it, like in your fluids class, something like that. Okay. Um, and I've got my equivalent Fourier's law equation, right? Which is just Q is equal to minus K. This is an area, right? So 2 pi r is a circumference of a circle, and then L is a length down the tube. So this thing represents basically a cylindrical shell inside my polar coordinate system, right? And then dTdr is just the temperature gradient in the r direction, right? So this should look familiar with maybe the exception of 2 pi r. Okay, so let's do our two integrations. Now, remember, way back when we did this for planar walls, I mentioned that I was going to leave the K in there, and then I immediately took it out. And I was like, this is going to become important later. So remember that I did this. I want to show you me doing it where it doesn't matter, and I'll show you later when it does matter. Here's the moment where it does matter. So I'm going to leave the K in there, at least for now, and I'm going to get a result that is actually going to be useful for something that we're going to use later. And then I'm going to just remove the K again, but we'll see that here in a second. So here I am integrating the derivative of that kind of inner term, right? So this term, right? I'm integrating that, leaving the K in there, and that's going to be equal to 0. And this dr comes across from the other side. So if you look here, right, I multiply both sides by r. So the r just goes away because that's 0. And then I take the dr over to this side, and that's me carrying out this integral. So I end up with k times r dt dr is equal to some constant of integration. And now, okay, here's the key thing that I want you to observe is that this combination of variables, kr dt dr, is independent of r, right? Why is it independent of r? Well, because it's equal to a constant, right? So even though there's an r here and an r here, if I put this combination together in this kind of product, it's independent of r. And what that means is that this expression for the heat flux, which we saw in the previous slide, right? This guy, k r dt dr, right? And 2 pi l, it's a constant, right? So thus, QR is independent of R, and that will become important later, right? So that's me just keeping the K in there so that you can see that this happens, so that we realize that this Q sub R is independent of R, and we're going to end up using this later on. But I wanted to just, show you and point it out here. Okay, so now what I'm going to do is I'm going to say, okay, I've got this proven. I'm now going to go back to this step, and I'm going to just divide, or I'm going to pull K out, right? Because K is a constant, and I'm going to divide both sides by K, and that gets me here, right? So K is gone. Um, and I'm now going to take my R and dr and I'm going to put it on the other side of the equation. And I'm going to integrate over T here and then over R here. And this is a constant of integration. So this from the previous step, right? So this comes out. And what I get is that temperature as a function of radius is equal to some constant of integration 1 times the natural log of R plus some constant of integration 2, right? So similar to the previous equation for a planar wall, except this is logarithmic, right? Instead of being just a constant value. So I'll point that out again when we actually look at the temperature profile. I did two integrations. I have two constants of integration. I have to put in two boundary conditions. So my boundary conditions are that the temperature at R1 is the surface temperature at 1, and the temperature at R2 is the surface temperature at 2. So I plug those in. I have two equations, two unknowns, C1, C2. I can solve these simultaneously. I'm not going to do it for you. You can do it if you want to just see how it works for yourselves, but I solve for C1, C2, and I substitute those results into my particular solution, and out pops this guy, right? So this is now my temperature profile inside the wall of a cylinder in polar coordinates, right? And I want just to point out, right, that T as a function of R is logarithmic and not linear, right? So remember before, when we were in a plane wall, this was a straight line, and now it has a very slight curve to it. That very slight curve comes from the fact that I've got R sitting here inside the natural logarithm, right? So that's where that difference comes from. I can now take this and plug it into Fourier's law, right? So Fourier's law, remember, I'm taking the derivative with respect to R. So I go through, take the derivative with respect to R comes down to the bottom, and I get this expression for Q. And now here's where that thing that I showed you before, this thing, becomes important, right? So remember, since Q sub R is independent of R, we can use the alternative conduction analysis. Remember this alternative conduction analysis and come up with the same result, right? So very powerful thing happens in science and engineering. We can get to the same result through different methods. You can solve for things that you couldn't otherwise solve for. So this conclusion is quite important because this ends up getting used in a lot of polar coordinate heat transfer problems where there's something that you don't know and you could actually solve using the alternative conduction analysis and then go back and find things that you didn't know in Fourier's law. So again, just want to point this out to you. This is a technique that you might encounter and might end up having to use in, for example, homework or like a future quiz. So I can go through it. I can say, okay, I know that QR is a constant. And so I'm going to play the same game that I played before with my alternative conduction analysis. Since Q is a constant, it comes out of any integration that I would do. And so I'm going to just take this. I'm going to move R and dr to the Q side of the equation. And then I'm going to take everything that's T, which is T is all by itself, to the other side of the equation. And I'm going to just integrate from R1 to R2 on the left. And I'm going to integrate from T surface 0, or sorry, T surface 1 to T surface 2 on the right. And end up with this exact same result, right? Is what pops out of that. So just an alternative way of getting to it. The other thing that I want you to recognize is if you look at this equation, it looks just like, if we go back somewhere, right? It looks just like this, right? So I've got a Q, I've got a temperature difference, and I've got some, combination of other variables that are important to the geometry of that particular problem, just sort of sitting out either below in the denominator or in front, right? So let's go back here. And what that implies, oh, there we are. What that implies is all of this stuff that's not Q and that's not T, that's a thermal resistance, right? So I can do the exact same thing that I did before with the plane wall, and I could say, okay, ln of R2 over R1 divided by 2 pi Lk, that is a thermal resistance for conductivity. And so I can use that to come up with now a circuit analogy for polar coordinates analogous to my circuit analogy for XYZ coordinates, for Euclidean coordinates. So I say here, from previous electrical resistance analogy, cylindrical wall thermal resistance is this, right? And so we can play this game, right? Where I've got now a composite wall that's made up of different cylindrical shells, all just one kind of stacked within the other. And just like I did before, I can come up with a thermal circuit analogy between all of these, right? So these are all resistances associated with conduction through these cylindrical shells. And then each one of these little temperature locations, right? These are all internal temperatures that are the interstitial temperatures between these shells. And just like before, I can add them up to get a total resistance. And from the total resistance, if I know the heat on the far inside wall and the far outside wall, sorry, the temperature on the far inside wall and the far outside wall, I can figure out the heat flux through this thermal circuit, or the other way around. If I know the heat flux, I can figure out the temperatures at all these different points, right? So all the same tools that you have to solve for voltages and currents in a electrical circuit, you can also apply to a thermal circuit in polar coordinates. And the same also is true in spherical coordinates, although I'm not going to do that for you. It's in the book. But you can see this actually is a very, very powerful technique that you can use to come up with all these different temperatures. So the other kind of thing that I want to mention is previously I had introduced this U value, this thermal conductance value. In this case, each one of these areas is different, right? In the plane wall, all the areas were the same. And so when I wrote this version of the equation, I was able to just pull the area out, multiply it by R total, and it made sense. In this case, each one of these areas is different, but the thing that's the same is that the heat flux through all of these layers is all the same. And so it turns out that the conductance through member one times the area of member one is equal to the conductance through member two times area two is equal to the conductance through member three times area three, and so forth. And that all together equals the inverse of the sum of all the resistances together, right? So again, when we do heat exchanger design, this is going to be important because in heat exchanger design, a lot of times you have like tubes that are carrying heat, or like fluid that's hot, and then there's some cold fluid that's on the outside, and they're trading heat with each other, and you end up calculating U values instead of resistances. So I just want to point out that this is here, so that when we get to heat exchangers, you'll recognize what these U's are, what they represent. They're just the inverse of resistances, right? And it turns out that U is defined by just one of these areas, but that selection is arbitrary. So you can basically take any one of these and pull out the equivalent U, and then you just have to multiply by the right radius, and you get back to the appropriate U value. So you can kind of see that here, right? So here, I'm getting rid of the area, quote unquote, but what is the area? It's just 2 pi R1 times L, right? Each one of these has a 2 pi in it. Each one has an L in it. So when I pull out that area, I pull out an R1. And so this lead term in the denominator has no R1 in front of it, but all these other terms have this R1, 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 R1. Those are all in there to compensate for the fact that I pulled it out here, right? And then they all get added up together in the denominator, and then I have this value for U1, right? So that's where U comes from. We'll come back to this when we talk about heat exchangers. But the kind of key big takeaway message is you can make a resistor analogy in polar coordinates the same way that you can make a resistor analogy in Euclidean XYZ coordinates, and you can use the same series and parallel resistor models that you had from circuits to model the heat transfer in this configuration. Okay. I did mention at the very beginning that there's this thing called critical radius. I'm not going to talk about it because the quiz that you guys are solving right now is very heavy on critical radius, and I want you to like discover critical radius as you're solving the quiz. It's derived in the book and explained in the book. So if you're confused about it for the quiz, please check out the book. But I will just mention that the critical radius of insulation is where the total resistance is minimized, and it's equal to the conduction coefficient divided by the convection coefficient for a cylinder. And then it's actually 2K over H for a sphere. Okay. So next subject, conduction with thermal energy generation. So we've managed to march our way through at least plane walls and cylinders, and by extension spheres, although I didn't talk about spheres, for one-dimensional heat transfer, conductive heat transfer, without any uh, thermal energy generation inside the wall. You can run into a situation where the wall is generating its own heat. It's generated not spontaneously from nowhere, right? The first law of thermodynamics obviously applies here, but it's generated, for example, in a situation where you've got electricity running through a wall and you have joule heating, and so that electrical work is being converted into thermal energy. Um, Okay, so I say here, consider the impact of Q dot gen triple prime, right? So this is a heat generation per unit volume on internal temperature distribution. There are cases where thermal energy is generated via conversion from some other form of energy, like electrical energy, getting converted into thermal energy, like I mentioned before. So common one, which I mentioned, is conversion of electrical energy. So E dot sub G into thermal power, which is Q dot gen, in a current carrying medium, so joule heating. And you guys know from circuits what that looks like, right? So if I'm interested in thermal power, it's just I squared R. I is the electrical current, and R is the electrical resistance. So I squared R gives me a power. And if I'm interested in the amount of heat that's getting generated or dissipated by something that's carrying electrical current per unit volume, I just take this electrical power, which is equivalent to the thermal power, right? Because it's joule heating, and then I divide by volume, and so that's how I come up with this value for Q dot gen triple prime. If I know, for example, the volume. Resistance, electrical resistance, and current running through my object. Okay, so um, we're going to go all the way back to the beginning, right? Remember, we have that three-step process where we solve the generic differential equation, we plug in the boundary conditions to get the particular solution, and then we take the particular solution for the temperature field and plug it into Fourier's law, and out pops the heat transfer. We're going to do the same thing, but now we're going to do it for Poisson's equation instead of the Laplace equation. If you remember the difference between Poisson's equation and Laplace equation, Laplace equals zero, and Poisson's equation, there's this generation term in there, so it's not equal to zero. And like I said before, this gets really tedious, and so I'm going to just do it one time so you see it done. But there's a set of basically cataloged equations in the appendix of the book, which I'll point you at here in just a second, which shows you all of the other geometries and all the other boundary conditions. They're all just cataloged. So you will not need to do this, but I think it's important for you to see where the equations come from so you can see where they break down. So I'm going to do it, just one time for you. Okay, so we're going to take Poisson's equation. Again, it's a second order derivative in space. So I need two boundary conditions. I have a plane wall. This is the exact plane wall that I've been talking about before, right? So it's got a hot convective boundary condition on the left side. It's got a cold convective boundary condition on the right side, and there's some temperature profile on the inside. This temperature profile is no longer just a straight line. Why? Because I have heat generation on the inside, right? Because I'm basically running current through this thing, perhaps, and it's dissipating heat as it goes. So notice, right, it actually gets hotter on the inside of the wall than it is even here on the hot side for the gas. And so I need to figure out what the shape of this temperature profile is. It's no longer a line. And so I'm basically solving now Poisson's equation to figure out the shape of this curve. Okay, so my two boundary conditions are, and notice before I had x equals 0 at the far left side of this. Here, I'm going to put x equals 0 in the middle. And there's a reason for that, which you'll see on the next slide. So x equals 0 is in the middle. This thing has a thickness of 2L. So the right side is L, the left side is minus L. My boundary conditions are the temperature at x equals minus L. So the far left side is T surface 1. And the temperature at x equals L, the far right side, is T surface 2. I'm not going to go through the details of doing the integration. Presumably, you guys have taken the differential equations class. You know how to do this. So this guy gets integrated twice, and it ends up looking like this once I put in these two boundary conditions, right? So this is the equation for my temperature profile inside this um, one-dimensional planar wall with the heat generation term kind of sitting out here as the lead coefficient, right? So, and as you would expect, right, this is very clearly a parabolic shape. And yes, in fact, it is second order, right, raised to the second power with respect to x, which gives you the shape of a parabola, right? So it does check out, even though I'm not going to show you how to do it, it does check out just kind of qualitatively. Okay. So, another situation, which is kind of a special case, is if we have a symmetrical boundary condition. So here we had two different temperatures on either side of this plane wall. Here we have the same temperature on either side of this plane wall. So these boundary conditions, T at x equals minus L and x equals L, are the same temperature. So I'm going to solve this guy again, right? Integrate twice, putting these boundary conditions, and out pops this much simpler version of the temperature profile, which you sort of expect because all of these terms are basically the same, and so they cancel out. And so you end up with this guy, which is also parabolic. The thing that I want to point out here, the reason that I mention this, even though it's like a little bit redundant, is at this spot, if I take the derivative at this maximum temperature spot, the derivative of temperature with respect to x is 0 at that spot. Because dt dx is 0, that means the heat flux is 0, right? So there's no heat flux at x equals 0. And because there's no heat flux at x equals 0, this kind of symmetrical situation can also be modeled as an adiabatic wall, right? So this solution that we get, where is it? This solution that we get is true both for a symmetrical convection situation and for a situation where the wall, instead of being 2L thick, is just 1L thick, and the far right side of the wall is covered with an adiabatic coating that prevents heat transfer. Hence, the temperature there, the derivative of the temperature is 0, right? Because you can't transfer heat through an adiabatic boundary condition. So I just thought that was cool. It's just a neat little kind of calculus trick where you can use one solution for two different configurations. Okay, so like I say, you could repeat this process for every situation to obtain a particular solution for every single permutation of every equation, every geometry, every set of boundary conditions. And we would be here until the end of time doing all that because there's so many different combinations. And so the book has very conveniently given you Appendix C, which is here. So available in the back of the book. And just, this is sort of frightening. I don't normally do this, but let's see if it'll work. Can I get out of this? Nope. Hang on. Let's see if yeah, there we go. Okay. So you should be looking at my screen now. This is Appendix C from the textbook. I intentionally pulled these pages out of the book and I dropped them into Microsoft Teams. So you can see here, right? Just like I said, temperature distribution, plane wall, cylindrical wall, etc., for all of the different things that you might want to solve for: temperature, heat flux, heat rate, different geometries, with generation, without generation, different heat boundary conditions, cylindrical walls, right? So it's like everything that you could want, like every equation is in this appendix. So it's dropped in Microsoft Teams in the same folder as this lecture so that you can get to it easily if you don't want to thumb through the book to try to find it. So that's there for you guys. But I'm not going to do any more of these because you can just now look them up in this appendix, and I think I've kind of beaten this to death. Let's pull this back up. Okay, good, good, good. Okay, so let's solve a couple of example problems. Okay, so here's example one. So we have some mass of water, which is initially a liquid, and it's at its fusion temperature, right? Which means it's um, not melting temperature. Well, it is actually the melting temperature, but it's also the solidification temperature, right? So this is liquid water about to turn to ice. Um, 273.15, is that right? Yeah, no. Let me check on this. This is should be 0 Celsius. Yeah, that's right. 273. Yeah. Sorry, having a senior moment. Yep. Okay. So it's at 273.15 Kelvin. So about to turn to ice. And it is enclosed in a cubical container of width 102 millimeters on a side. No idea where that number came from. So the width, this is a square or a cube, 102 millimeters on a side. The container wall thickness is 5 millimeters, so this thickness 5 millimeters, and the thermal conductivity of that material is 0.05 watts per meter Kelvin. The outer wall surface is suddenly reduced in temperature to 243.15 Kelvin, so minus 30 Celsius, right? And when I was originally given this problem, these are textbook problems. It was all in Celsius, and I am doing the work of converting it to Kelvin for you, just so that you don't get confused. But always, 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 if you have temperatures in Celsius in the world of heat transfer, please convert them to Kelvin so that you don't end up multiplying or dividing by degrees Celsius and getting yourself messed up, right? I'll try to do it for you, but out in the real world, everything is in Celsius. So just remember to convert everything to Kelvin so you don't run into mathematical hardship from not using absolute values or absolute temperatures. Okay, so we've got suddenly this wall is suddenly reduced to 243 Celsius Kelvin, resulting in water solidification to ice. And we're given the HSF value, right? So this is the latent heat of solidification for water, 333 kilojoules per kilogram. And then we're told that a thermal contact resistance develops at the interface between the solid wall and the ice as the solidification progresses, right? So we basically got liquid water in this cube, and we all of a sudden drop the outside temperature. And as a result, there's going to be some heat transfer from inside of the cube to the outside of the cube, and that is going to cause solid ice to form from the liquid water that was in there. And what we can see here is like the beginning of the formation of that layer of ice. And so we're asked then to determine the interfacial thermal resistance, R double prime, shortly after the onset of freezing, and we're told to do it in units of meter squared Kelvin per watt. And then we're also told that the initial solidification rate, M dot, is 0.05 grams per second, right? So that's the rate at which the ice or the water, liquid water, is solidifying into ice. Okay, so how do we tackle this? First, we have to make a couple of assumptions. So first assumption is we have a linear temperature distribution in the walls, right? This is not a 1D problem, right? This is a cube, right? So there's definitely three dimensions here. So we are making an underlying assumption. We're going to treat the heat transfer through all the walls as if it's one dimensional. We're going to ignore all the corner effects and all the two-dimensional effects. We're going to treat this as one-dimensional heat transfer. So linear temperature distribution on the walls, and as I just said, one-dimensional heat transfer. Okay, the approach is that the through wall heat transfer is going to be equal to the heat transfer from the water, causing an isothermal phase change in the ice, right? So as the ice, remember back to thermo, as the ice, liquid water is changing phase from liquid to solid, that is a constant temperature process that sets the temperature inside the cube as the heat is getting transferred out. And so we know what that temperature is for this entire process. The reason that I picked this problem is because this is exactly what you guys are going to do in the lab experiment, the first lab experiment to measure conduction through a series of different materials. We are actually going to use the phase change of ice, in this case from solid to liquid, to set a constant temperature, and then use that temperature to back out what the thermal conductivity of different materials are that are essentially facilitating heat transfer from the ice to a heater, right? So I picked this problem specifically because we are doing this in the lab. Um, Okay, so we have water changing phase, which causes an isothermal condition. And so we want to just write the equivalent thermal circuit, and we want to solve for this contact resistance. Okay, so um, I'm going to start all the way back in thermo with the first law of thermodynamics. Here's the first law. Here is my system boundary, which is just the water, liquid water that hasn't yet turned into ice. And I'm going to say that the change in energy is equal to Qn minus Q out plus Wn minus W out. This is the full-blown version of the first law of thermodynamics. I got a lot of comments about, well, isn't it just Qn minus W out equals delta E? And okay, yes, that's perhaps true, but that is the version of the first law of thermodynamics for like a power cycle, right? So this is not that, and so I'm going to draw it out, write it out in its entirety so that I don't miss any terms. Um, I do not have heat flux in, right? The heat is leaving my control volume, right? So this term is gone. And I do not have any work transfer processes, so these two terms are gone. What I end up with then is that the change in energy of my system is equal to just the heat that's leaving. So this negative sign comes from the fact that this is the Q out term. The change in energy of my system is the amount of energy that's basically being given up by the solidification process, which is m dot. So this is the solidification rate times the latent heat of fusion for ice. Both of these values are given. So here's that value of the solidification rate, and then here is latent heat. Notice, by the way, this was given previously in kilojoules per kilogram. I'm just making it in joules per gram, right? Just for no reason other than this value was given in grams, and so I put this value in grams, so I don't have to do a lot of conversions. Okay, so multiply these two by each other, and I solve, and I get Q out is equal to 16.7 watts. Notice the negative sign is still there. That negative sign came from here, which came from here. This is a Q out term. This negative sign is there because it's heat leaving, or thermal energy leaving my system, right? So that negative sign will become important later. So don't forget about it. Um, Eventually, I want to turn this into a heat flux, and so I'm going to find the total area across which all this heat is leaving. I have a cube. The cube has 6 walls. Each wall is a square with an area W squared, and so this is the total area of my cube calculated there. And then I'm going to take my thermal power. I'm going to divide it by my area, and that's going to give me a heat flux, right? So here I am doing that, and I get 267.5 watts per meter squared units of heat flux. Notice that negative sign is still there, right? That negative sign came from here, which came from here. Okay. Now, um, I need an expression for what this heat flux is. So fine, I'm going to use my thermal resistance model. So I know that Q dot double prime is equal to T1 minus T ice. Notice I'm doing this on purpose. T1 is colder than T ice. And so this thing should be negative, but this is the convention that we use, right? So whatever the far downstream temperature is always gets written first, and whatever the upstream temperature is from which the heat is coming gets written second. And so you can see very quickly this is going to be a negative number, which is why I needed that negative sign to stay in there, right? So it all does actually work out if you account for it in a self-consistent way. So this temperature gradient divided by some total resistance is going to equal that heat flux. What's the total resistance? Well, it's the resistance associated with the contact resistance between the ice and the wall. So that's this R double prime that I'm looking for, and then plus the resistance to heat transfer presented by the wall, right? So you can actually see it here. Here's my thermal circuit. Here's T ice, the temperature of the ice. Here's the heat flux. And here's T of the outer wall, which I set at 30 Celsius, minus 30 Celsius. Here's the resistance associated with the um, uh, ice interface. Here is the resistance associated with the wall. They are resistances in series. They get added up. So they're added up here to give me R total. So I take this R total, I put it in here, and then I'm just going to solve this guy for R double prime, right? Because that's what I'm actually trying to isolate. So R double prime is sitting here all by itself. I rearrange everything so that I've got everything known on the right side of the equation, the thing I'm solving for on the left side of the equation, and now I just plug in numbers, right? So here's my wall temperature, here's my constant ice temperature, here's my heat flux, negative sign is still in there. I'm subtracting away um, this L over K. It's very small, but it's there. And I end up with a resistance here of 0.0121 watts, meter squared per Kelvin. Let's try again. 0.0121 meters squared Kelvin per watt. There we go. And I check this against the book, and that is the correct answer. So we get a green check mark there. Okay. So that's that one solved. Next problem, last problem, is example number 2. So we just did XYZ Euclidean coordinates, and now we're going to do polar coordinates. So I have a 3 millimeter diameter electrical wire, which is insulated by a 2 millimeter thick rubberized sheath, whose K value is given 0.13 watts per meter Kelvin. The wire sheath interface is characterized by a thermal contact resistance. So here's another one of these. Thermal contact resistance comes up a lot, right? It happens an awful lot in the real world. R double prime of 3 times 10 to the minus fourth meters squared Kelvin per watt. We're told the convection heat transfer coefficient at the sheath outer surface, so that's out here, is 17 watts per meter squared Kelvin, and the ambient air temperature is 293.15 Kelvin. If the temperature of the insulation may not exceed 323.15 Kelvin, that's 50 Celsius, what is the maximum allowable electrical power that may be dissipated per unit length of the conductor in watts per meter? And also, what is the critical radius of the insulation? There's that critical radius thing again. Okay, so how do I tackle this? So I've got my schematic here. This is a figure borrowed from the book, which I didn't actually use anywhere else, so I figured I could use it here. The inside wire is represented by kind of this gray cylinder, which is generating heat because it's got current running through it, right? So this is my generation term. And then this kind of outer rubber sheath is meant to be represented by this dotted line that looks an awful lot like a control volume. And it actually is a control volume, but it's also representing the sheath. I'm in polar coordinates, right? So I have a R value in the radial direction. I didn't put it in this figure, but I think I ended up calling, yeah, R outer and R inner. I think are what I used for the insulation. Okay, so same game as before, right? I'm going to treat this as one-dimensional conductive heat transfer, and I'm going to write this thermal circuit, recognizing that all of the heat that gets generated by the current running through this wire has to get dissipated out through the rubber sheath. And so here is my thermal circuit. I have the temperature of the inner wall. I have that contact resistance between the inner wall and the rubber sheath. I have a conductive resistance, which is presented by the conduction through the sheath itself. And then I have an outer convective heat transfer resistance, which is from the outside wall of the sheath to the outside environment, which recall has a fluid blowing over it at some T infinity and some H value, which are given, right? So here's my thermal circuit. Just add all these things up, and that gives me my total conductance. Okay. So, oops, I did this in the reverse order. Sorry, I meant to describe this second, but I described it first. So we're going to make some assumptions. Everything is in steady state. We have one-dimensional radial heat transfer. All of my properties, things like K, are constant for all my materials. And then heat transfer to the surroundings is dominated by convection, so I don't have to worry about any radiation coming off of that surface, right? Just simplifies that boundary condition. So my approach is going to be to write the thermal circuit, which I already talked through. So write the thermal circuit, solve for the heat transfer. This should say Q prime sub R. Whoops. Okay, I'll change that. Q prime sub R for the maximum tolerated insulation temperature. And then we'll evaluate the critical radius because we're asked to do that. And I still haven't explained what critical radius is. I'm not going to in great detail, but at least see how it's done. Okay, so just like before, I'm going to start with my first law of thermodynamics. My control volume is the outside wall of the insulation. So it's basically just this dotted line. And here's the first law, delta E equals Q dot in minus Q dot out plus W dot in minus W dot out. In this case, I'm in steady state, so I have no change in internal energy for my wire, no energy stored, right? So that term is zero. I have no heat entering, so this term goes away. I have no work leaving, right? So this term goes away. I'm definitely conducting heat out. So this term stays, right? The negative sign is there because it's leaving. And then, whoa, where did this come from? Well, I'm putting electrical power into this wire by running current through it, right? And if you remember back to thermo, electrical power is a work input, not a heat input. And so this term cannot be taken away, cannot be removed because I am actually doing work on my system, electrical work on my system. So this term stays. So with everything else canceled, I end up with just that W dot in is equal to Q dot out. And W dot in, this is my electrical power in, which we described before as just E dot sub G. Notice this one prime because I'm now doing it on a per unit length basis because that's how I was asked to solve it. And then this Q dot out is just the heat transfer in the radial direction, again, prime representing per unit length. Okay, so we've now got this expression and we have to figure out the temperature that the insulation will tolerate, right? So this is the temperature that we care about. It's the temperature of the insulation on the internal surface of the insulation in contact, reasonable contact with the outer surface of the wire. So this is the temperature we care about. This is what we want to solve for to make sure that this does not exceed 50 Celsius or 323.15 Kelvin, right? So this is the temperature we care about. Now, this problem had a contact resistance in it, right? There it is. And what about that contact resistance? Do we care? No, it's a trap. Haha, Admiral Akbar. Why? Because that contact resistance happens downstream of this temperature that we care about, right? So yes, certainly the heat flux from the wire passes through that contact resistance to this spot, but I don't need to know anything about this contact resistance because I can use all of the, skills that I have from my circuits classes to just solve for the temperature difference from here all the way up to here and just completely ignore this contact resistance. I don't need it, right? And you might be saying to yourself, "Oh, but come on, Dr. Traum, like this insulation is actually touching the wire, right? Okay, fine, contact resistance, but it's actually touching the wire. And so, even if this temperature kind of in a bulk sense is below 50 Celsius, there's contact there, right? So it's going to melt. No, right? Remember this picture that I showed you before for contact resistance. There is the heat that comes in from the wire, which is here, and then there's a big jump in temperature from this temperature field to this temperature field. And that's what we're taking advantage of to allow this to be 50 Celsius or below where the wire is hotter. This contact resistance actually causes a jump in those temperature values. And so the wire can be hotter than 50 Celsius and the insulation will not be hotter than 50 Celsius because of this jump. So, it's a trap. Okay, so here's my equation, right? So I'm just taking the heat flux from here all the way through to here, right? So here's my temperature at the insulation that I care about. I'm solving for this. And here's my temperature at the outside surface of the wire. And I have two resistances. I have one that's a conductive and one that's a convective. So you'll recognize these are the resistance for conduction and the resistance for convection in polar coordinates. This one is the insulation outer radius divided by the insulation inner radius. Note that they are radii, not diameters, right? Don't mess that up. You might get the wrong answer if you're not thinking about radii. So all I have to do now is just solve this guy for this heat flux per unit length that gives me a temperature of 323.15 Kelvin at this spot. Again, protected by the contact resistance from the higher temperature of the wire. And I know everything else, right? I know these radii, I know the K values, I know the convection coefficients, I know everything. So I'm just going to plug it all in. And what I get is 8.08 watts per meter, right? With the units are correct. It's power per distance. And that is the heat flux that I can tolerate through this spot out through the wire before that insulation actually melts. And that means, right, if I go back to my first law, this is that heat flux that I just solved for. That is the electrical power that I can run through this wire before I start melting the insulation, right? So that's my value for electrical power. So that part of the problem is solved. I forgot my green check mark, but yes, this is actually, oops, I forgot my laser pen too. There's my laser. A little too late now. Yeah, that's my electrical power, which is what I was actually asked to solve for. Okay. Um, oh, critical radius. This is the last thing. Okay, so again, if you're interested in critical radius, you'll learn a lot about it from the quiz. It's in the book. I'm not going to spend time explaining it now because you're basically being evaluated on it and you can find the information you need from reading the textbook. So I'll leave you to do that. But the critical radius for cylindrical coordinates is K over H. We know the K value for the insulation, right? That value for this is given. And we know the H value for the convective heat transfer from the outside surface of the insulation. That value is given. So I'm just going to put that ratio together and I get 0.00765 meters. And the important thing here is that this value is actually less than, sorry, let me try again. This value is more than the radius of the outer layer of the insulation. And so what that means is that I could actually thicken the insulation at least up to the critical radius, and thickening the insulation up to the critical radius would allow me to run more electrical power through the wire and still not surpass this 50 Celsius, 323 Kelvin overheat condition at this spot, right? So that sort of gives you a hint about what critical radius means. I can run more electrical power through, more heat through before I have to worry about this thing melting. Okay, so we've solved two example problems, marched through a pretty substantial uh, chapter in the book, right? Lots of sections. So that brings us to the end. I appreciate your time and attention, and I will see you in the next lecture. Thank you. Bye.